So last class we discussed about the possible causes of tsunami. Now we will discuss about the characteristics of tsunami. Actually, the damage which is due to the tsunami is mainly caused by two basic mechanisms. The first one is the smashing force of a huge wall of water. That means when a water is traveling, large waves are traveling from the sea to offshore. It's look like say a wall of water, a heavy wall of water, just a thrust force is applied to the adjacent offshore. So due to this high speed, it generated destructive huge destructive power, because here is a transformation from kinetic energy to potential energy. So due to this large amount of energy, the adjacent areas are damaged, and this is the first mechanism. And when immediately after the destruction, when this large volume of water is drained out from the land to the sea, that means the reverse process. In this process, it as it is a quick process, it's works like a it works like a debris flow. That means huge amount of water is flowing like a jet, and it collects all the adjacent materials, small buildings, houses, etc. So it's works like a debris flow is something like an, and when the soil, water, and other foreign materials are transported together with a high speed. This like force. And so this is the two mechanism. One is incoming and another is outgoing. That means at both stages of the wave, and water coming and outgoing, both stages are destructive in the case of tsunami. And in the large deep ocean, the wavelength may be up to 200 kilometers length or width, and the velocity of tsunami, that is can be calculated as we discussed some earlier equations. And finally, another thing, when tsunami approaches nears to the coastline, the water becomes shallow because the depth of ocean is reducing. So due to this, the water depth become shallow, and this can be decreased up to 80 kilometer per hour, and then speed is also reduced. Now come to the tsunami risk
স্যার
assessment.
এখানে শলিং দিয়ে কি মিন করছে স্যার?
Which one?
So this is shawling, wave shawling, compress the wave. So এখানে সেটা দিয়ে কি মিন করছে? এটা বুঝিনি স্যার।
Compress the wave and its speed decreases. That means the wavelength is larger. That means the gap. Okay, and when it is in the deep sea, the gap between the wave peaks are larger. That means after a certain time, one peak is coming, then another peak. But when it comes to the near to the seashore, in that cases, the waves are coming to cumulative. It is a general trend. When you go for any normal seashore, you may also find this. The wave height also decreases and the intensity is increasing. That means the time period between those are decreasing. That means this is looking like something the waves are compressing together while it's moving towards the shore. Okay. So this is that kind of phenomena. And now come to the tsunami risk in Bangladesh. That means we are now up to the last slides. We discussed about the general causes of tsunami, its effect, how it is generated, propagation, etc. Now based on the tsunami risk and the vulnerability and potential seismic source along the coastline, the geological pattern and survey of Bangladesh. Overall, the Bangladesh coastal belt is generally it is divided into three zones. The zone number 1, 2, 3. The first zone 1, this is in the Chittagong Teknaf coastline. And the zone 2, this is the Sundarban Borishal coastline. And the third zone is the tsunami vulnerable zone 3. This is the Borishal Sondip coastline. Okay. So this is, and the zone 1, this is highly most vulnerable zone. And because as we discussed in our earthquake risk assessment and details in the seismic characteristics in Bangladesh, along the Chittagong Teknaf hilly region, and this along this coastline, some active tectonic plates, tectonic interfaces are also found between the India Myanmar tectonic plates. So and the another one is Andaman Nicobar fault system, which is also capable for generating tsunami in the deep Bay of Bengal. So due to the all of these reasons, the Chittagong Teknaf coastline, this is considered the most vulnerable among other two. And the next one is the Sundarban Borishal coastline, and in those region. In those regions, these are actually moderate vulnerable because comparatively the earthquake risk and vulnerability is also lower in those regions. This is actually directly related to the vulnerability of earthquake or seismic activity. And the last one is the Tsunami in the Borishal Sondip coastline. This is the less vulnerable area due to the presence of shoals and uprisms. Okay, so next, this is the graphic map representation of tsunami vulnerability zone, and here the zones are noted as 1, 2, 3, and in Khulna region the vulnerability is also low due to the mangrove forest system, because in this zone, that means in zone 1, if I mark this in the zone 1, this zone actually this zone is directly open. These shores are directly open. That means, and in these areas, the locality are very close to the seashore. So the vulnerability and possibility of damage is also higher compared to those others, because in these areas actually here. A huge area are overlapped with the due to the mangrove forest. So these mangrove forests are also passively work as a barrier. Okay, later we will discuss how to tackle the tsunami and preventive measurements. So this mangrove forest is passively worked as a those types of barrier walls, like natural, something like natural barrier walls. So walls. So these areas are less vulnerable. And next, the warning system, the tsunami warning system. So this is a technique to detect the tsunamis and give some warning in advance, as the tsunami is generated in the deep sea, so it moves from deep sea to the shore, and when this tsunami comes hit to the coastal lines, so this is the starting of damage. So there have some time from the generation to its damage. So due to this gap, it's sometimes easy if we can develop a warning system. And this is actually let us see two different types of warning system. Actually, first one is the international and another one is regional. This is very simple, because if our warning system only capture the tsunami and for a small area, or certainly for a country, so these are the general, and if it interact with the data of the international warning system, so this will be termed as the international system. So let's see the arrangement. This is actually both are actually same. Just I am this some of the schematic diagram. I'm simply describing this. So here is actually pressure sensor in the seabed. Okay, pressure sensor. Pressure sensor is too much sensitive, so that it can measure the 1 centimeter height of water. The work of the pressure sensor, this function is to simply calculate the load of water above it. That means suppose for in general condition, for a general ocean, there is a certain level of water. That means the depth of water is almost more or less fixed, depends on the location, or also for the season. That means in a rainy season, the water level will be some higher compared to the summer. So there is a conventional depth of water is known in general from the previous data. You may identify, okay, this will be the general depth of water conventional for this location. So if we put a pressure sensor in the seabed, and it will measure the pressure. That means the depth, the pressure is actually pressure of water is directly related with the depth of water. Okay, that means mgh or some other equation. So if we know the pressure for this point, suppose now for any reason the tsunami is generated in some location of in the deep sea, and the waves are coming like this. So when a large wave is passing through this above this point, the pressure sensor can measure the weight of water column above it. That means the pressure will be, overhead pressure will be increased as the water depth is increasing. Suppose like a single wave is going, okay, passing this, and then next wave is coming, and this also passing above this overhead line. So when the water successive number of waves are passing, it records huge pressure after a certain period. So this is the record, and this the pressure sensor data, this will be transmitted to a local data recorder. That means this one is actually a GPS antenna system. That means this from ocean bed to this point, and this data will be transmitted, and thereafter from this point the data will be transferred through the satellite, okay, to the different ground stations. That means in the shore or other meteorological departments or other positions. So this is the basic the arrangement, and this data center, the local center, this is also anchored with the seabed with some anchoring system. And so this is the overall arrangement based on the very basic elements. So this is the tsunami early warning system arrangement, and next one is the tsunami risk reduction. So the tsunami risk reduction, this will be actually depends on the hazards, how the hazards will be occurred, or the susceptibility of tsunami hazard. Basically, the topography of the certain area, sea floor, and topography of the coastal area. These suppose if we consider the our Marine Drive road from Cox to Cox Bazar to Inani, in those areas. The coastline contains a series of mountains. So if moderate or less strength of tsunami is occurs, so this mountain can be interact like a natural barrier system. On the other hand, if there is a locality, so the risk or possibility of hazards will obviously higher. Okay. And the vulnerability can also be, as we discussed earlier, the development of map potential risk. Comparing the potential risk, we can develop a map. That means which areas are comparatively vulnerable for the tsunami hazards. And previous tsunami history, and with its associated coastal community damage, these records are also helpful to understand the tsunami risk for the future. And next one is the avoid of new development in the tsunami runoff areas. That means while tsunami are coming, it's a certain thrust force, and when the force is and the water is going back, it covers a certain area. That means it's like a flash flood. That means works like a flash flood, a certain area throughout the certain areas. The agriculture, park or locality, all small structures, all these things will be carried out. So based on this things, while we are going to developing a new area, if we consider that in our Cox Bazar, Technaf, in along these coastlines, new communities, hotels, recreation centers, okay, then the resort, etc., are ongoing, continuously ongoing. But none of us are worried about the future. Suppose if there is any susceptibility or vulnerability of upcoming tsunamis within next 50 years or within next 100 years, so what will be happened? Okay, so no risk assessment is done before constructing any new locality. So this is another factor. And next one is the let's see, three figures. And so these are the different configuration and arrangements to develop for the minimization of the tsunami losses or risks. So first one is the avoid the inundation areas. In all along the coastlines, there may be undulations. So while you are choosing your positions, you need to avoid the lowland. Okay, this is useful for the newly developed lands from ocean, some new island. If you consider, in those cases, we need to always take some safety for this tsunami. And most of the coastal structures you may find that those structures are constructed leaving the ground floor empty. That means there is only columns. You can easily find this in the primary schools, cyclone centers, etc., in the coastal areas. So this is a technique to avoid the inundation. Suppose you need to there is no high land, sufficient land having sufficient altitude. So what can be done? In that case, you can simply elevate your structure from the ground surface, so that if the tsunami flash or jetting effect is coming in and coming out, so there is only some few columns, there is no wall in the ground floor, so the water can easily come and go away. So in these cases, there is no risk, or the risk is comparatively reduced. But if you put some wall in the ground floor, that means if you used this as a conventional building, in that cases the water force will hit on your walls, it will causes sufficient damage, and while going out the water, it also provided thrust towards your building. So this is the first one, to avoid the inundation area, or to build in the high ground or the elevated buildings. The next one is the slowing water currents. This can be the first figure. This can be done by providing some putting some sheet piles like things, or something like walls having different heights. That means some random structures, or this is very similar to the mangrove forest or a swamp forest. Mangrove forest exactly serve the same thing, for showing in the figure 1. So this reduce the the wavelength and also the wave intensity along the coastal belt. So due to this, your building will having the less effect, or building will be safe. And the next one is the steering. So steering is an technique, actually something like bypass wall. That means if you have already constructed structures, so to prevent this from the upcoming tsunami, what can you do? You can simply put like a boundary wall having the converging face or angled face. That means the water can simply bypass through the two sides of your building. So this is the steering technique, steering of the water force. And the next one is the blocking water force. This is something like a barrier wall, simply like a retaining wall. So along your coastline or along your building, if you put a blocking wall for a certain length along the seashore, so the water will be directly hit on this blocking wall and will go reverse. But it's actually costing it's not like a cost effective, because this wall need to face a huge amount of water thrust, okay, a large water thrust, water wall pressure. So this is not like a simple brick wall, or not like something a simple wall. So these walls need to resist a large amount of pressure, okay. But on the other hand, this wall will face the pressure. But on the other hand, these buildings, although the water may enter throughout the side or other sides of the walls, but this building will save from direct water jet, okay, and direct scouring of the tsunami water jet. So this is another technique. This is some conventional techniques. And next, the some construction and preventive measures. That means to build a heavy rigid structure, high rise, not for opening, as I discussed earlier, the opening, the ground floor opening, and the perpendicular orientation perpendicular to the shorelines. That means if you construct a building perpendicular to the shorelines, that means the thickness, width of the building along the shoreline is less. So in that cases, the effective wall area for the water thrust is less compared to the opposite condition. Suppose you are construct a building along the shorelines. In that cases, the long direction or long face of the building is exposed to the ocean. In that cases, as the area is higher, so the water thrust will also higher. So this is another technique. And here are also some other preventive measures and some critical structures like water plant, hospital, etc. Those are need to be construct some away from the coastline, because in case of emergency, so that those can also be operated to reduce the risk of the locality. And next, the calculation of tsunami magnitude and damage evaluation. So this is a typical chart, which the first equation shows the tsunami magnitude based on the directly on the earthquake magnitude 2.3 multiplied by m minus 16.20. In this case, this magnitude is directly from Richter scale magnitude. If you put this Richter scale magnitude, so the tsunami magnitude for those specific earthquake, it can be easily calculated. And the next one is the tsunami magnitude scale from -1 to 4 based on the visual runoff height. That means the visual wave height, water wave height, based on this magnitude scale is done from -1 to 4. Suppose for if the visual runoff height is 1 to 2 meter, so the tsunami magnitude will be taken as 1, and corresponding possible damage is like the fishing boat damage. Similarly, the magnitude 2, 3, and 4. If the visual runoff height is greater than 30 meters, that means water height is greater than 30 meters. 30 meters means tentatively building height of 10-story building height. So if the water is level is such high, the wave height, visual wave runoff, in that cases, the tsunami magnitude will be 4, and the possible susceptibility is more than 500 kilometer area damage. That means here is the possible damage are also listed. So this is an typical explanation of tsunami magnitude. And next one is the tsunami and the deep ocean and the process. Here are some explanation, and I'm not discussing those. This is some theory. And next, the some effect of tsunami. Here are some basic effects are also discussed due to the tsunami. The cars, small structures, these can be moved away. Okay. and waves of half-meter high can tear the building off and the foundation. That means the scarring in the foundation level will occur. And some other typical damage. All of these are actually known to us. Damage can also wave flows and flow in and the flow out. In both cases, the damage can occur. So these are the very common things. I think you can just go through some reading and you will understand this. Here is the community effect. So these are some conventionals. Just go through reads. Now I would like to discuss some real case study of tsunami, and some I would like to visualize some real scenario. So in this case we considered a tsunami in Japan in 2011 in this area, actually in this area, this coastline. So these are the map view, and these are actually some scenario after tsunami. The building is still in its position, but here is a gap. So could you understand or guess the think what happened in this position? Okay, let's see in this area. So let's zoom in this. So this is the scenario. Okay. Here are some pile found. These are the pile foundation. This is the pile cap, and thereafter this is the building. Here is also some base isolation system for earthquake. So scouring. The effect is the scarring in this tsunami. Due to this tsunami, the scarring in the foundation level. That means as it is the deep foundation, so no possible damage are occurred. Just only the soil and the materials along the foundation levels are simply washed away due to the water moving out effect or the jetting flashing effect of tsunami. Okay. So this is one effect, and next one in this area. Okay, in this area, let's see. This is a building. If I show in the laser point, this is actually a building. Okay, and the dimension is building is around. This is the typical dimension: 12-meter height, 8.4 meter width, and 16 meter long. This is a building, and this building is uplifted, totally uplifted from its position and carried over 20-meter distance. That means the building having this dimension is moved away from its original position to a 20-meter distance. So can you imagine the force of water, the huge water force that actually thrust on these building faces, and thereafter this building is also a pile foundation, RC pile foundation, the pile foundation building, and due to this the piles are uplifted. That means the piles are RC piles are generally cast in situ, or in some cases precast piles, and when and this is connected to the as we see from the previous figures like this. The piles are generally the pile foundation is generally attached to the pile cap, and thereafter it's connected with the superstructure. So while this tsunami force is thrusted along the building face, due to it faces overturning effect, overturning forces, and due to these forces, and the piles are uplifted. That means the piles are uprooted from the ground, and at certain time these piles are disconnected from the buildings, and thereafter the building is moved away 20 meters from its original position. So this is can you imagine how many force are required? Actually, each pile is pulled 3 meters up. Okay, and if you consider later in the geotechnical engineering course 2, I think you will learn how to calculate the force for the friction, that actually the piles are working mechanism of piles are in the friction force. That means the interface between pile and soil, there is a friction coefficient and then multiplied by the surface area of the piles. So in that case, the surface area into friction coefficient, that will give you the force capacity per pile. So if I consider 3 meter is simply consider the 3 meter is pulled out and how many number of piles are in those buildings. So just simply multiply that huge amount of, you can imagine just the force of water. Huge amount of force is actually required to do such types of hazard. Okay, and this is actually a section of the pile cap. This is 5.6 meter by 5.6 meter area, and the circles are actually represent the pile head. That means these are actually for the precast piles, and then the pile heads are connected with the pile cap. So in these cases, 4.505 meter long precast pile. These are actually precast piles, are precast concrete piles. These are the pulled out 4.5 meters per pile. So here are huge number of piles. Simply considers how force are required to do this damage. So this is some visualization of real scenario due to tsunami. Now up to these slides, this is our discussion of tsunami, and now we have another two topics. One is the drainage basin. In today's class, I will only discuss about the some basic we'll simply discussed some basic parameters of drainage basin, and thereafter hopefully next week we will do some mathematical we'll practice some mathematical problems for drainage basin. So the first question, what is the drainage system or the drainage? For a river system of an area, this is called the drainage. The basic mechanism is that for any large river, it connected with some small rivers and its tributaries. Those are actually collect water from a certain area. Okay, that means from a certain area, water is collected by some small canal, then it transferred to a large canal, then it transferred to another tributaries to the small rivers, and then it's connected to the main rivers, and finally its water is discharged to the for Bangladesh, it is discharged to the Bay of Bengal. So this is the system, and for a river with its an adjacent area which is served, this is called the drainage basin. And for the river basin, the rain catchment area, that means the mainly it collects the water from the catchment area due to the rain catchment area. And during the rain or precipitation, a certain amount of water is directly infiltrated through the ground. That means some amount of water is absorbed by the ground. This is called the infiltration, and the remaining portion will be run off and move to the water body. So this portion is actually known as the runoff. So up to a boundary on which a certain river catch the waters is called the catchment area, or the basin for the rivers through its tributaries and streams. And the watershed, the smallest unit of a river basin, this is called the watershed. That means suppose for only a single canal of a river basin system, it collects the water. Let's consider, suppose for this small canal. These actually say this canal serve only a small area, so this will be called the watershed. And the drainage pattern, next we'll discuss about the pattern, different patterns of drainage, that means its visual classification. So these drainage patterns will actually depends on the local topography, that means the land sloping, and the geological parameters like the lithology, types of rocks, etc. The structure means here the fault joint, etc. That means the for the lithosphere, it's the fault line, the joints, etc. The climatic condition, also the rainfall or snowfall, etc. The vegetation, that means is it is a tree or the forest or the marshy land, or it's the urban area or rural area, etc. All these things actually all these things affect the drainage patterns. So let's discuss some patterns of the different types of drainage basin. So drainage basin, this is an extent or area of land where the surface water from the rain and the melting of snow or ice converts to a single point, usually the exit of the basin. That means actually if I have figure, okay, so suppose consider this one, this is the exit point of the basin. That means from this point the water is discharged to another bodies or in the ocean or any other position. So this is the exit point, and all the adjacent areas, suppose this area is served from this river, so this will be the its basin. Now let's have some look on the different types of basin. First one is the dendritic drainage basin, parallel drainage basin, trails drainage basin, rectangular drainage basin, radial drainage basin, centripetal, dearranged, annular, and angular. So these are the different types of drainage basins. Actually all these classifications are based on the pattern. Okay, different drainage pattern. The first one is the dendritic. This pattern is actually looking like a tree. Okay, if you consider look at this image, this is actually looking like a tree. Suppose for a tree, while you are moving upward, you will have some branch, sub branch. Okay, so this system is known as the dendritic patterns. And two tributaries meet at a point, then it meets to another one, and here are some V-shaped valley. Okay, result the rock types. So this is the dendritic pattern system. And next, if we move for the parallel drainage system, look at this image. The parallel drainage system is looking like this. That means the streams are parallel to each other, although it's like the previous one, like the dendritic patterns, but here the tributaries are parallel to each other. Okay, so for an example, a river flowing the southeast from the Mount Canyon, in this look, this is the real scenario from this area. So in actual cases, you may not find direct straight lines to straight parallel tributaries moving and then merge to one point. This may not be found, but this is the typical example. And next, trails drainage basin. This is actually found in the hill area. Suppose this is one mountain, two parallel mountains or lands. In those cases, the flow direction of water, suppose the flow direction of water is in this direction, and from ridge, this is the valley. Along the valley, the flow, the main tributary is along the valley, main stream, and its sub streams are will come from these two direction. That means this is one ridge and this is another ridge of the mountain. And so from these two sides, water will be collected and then move away in this direction. So this is the trails drainage system. In these cases, most of more or less tributaries enters to the main river more or less in 90°. That means, and here the meeting angle is more or less 90°. So these are the trails system. And here is the rectangular drainage system. The rectangular drainage system is actually developed on the rock that has an approximately uniform resistance of erosion. That means if the rock of a certain area, of a large area, these have a uniform characteristics and having some predefined crack or joint in the two directional joint. That means suppose in this direction two directional joint having in the rock, in those cases actually the meeting angles of the these tributaries are actually formed day by day due to erosion. So if it have the uniform characteristics and the joints are usually less resistance to erosions, in those cases these types of rectangular patterns, drainage patterns are created. And next one is the radial drainage patterns. Radial drainage patterns for mountain, the radial drainage streams from a certain point it's radiating outwards like this. This is a mountain, and if the waters are collected from these areas like these small tributaries and then radiating outwards. So this is the system like for the volcanoes or others. Here is an example for Kyushu, Japan, for a certain mountains. The top view will be looking like this. So this is the radial drainage systems. The water is moving outward from a certain point. And centripetal drainage system, this is opposite to the radial drainage systems. In these cases, there have a central lake or water body. In those cases, from the adjacent areas, waters are collected and through its streams and then discharged to this water body. And this created, and this can be create a beautiful look. This image is actually collected from Canada, from a lake. And next one is the annular drainage system. Annular means this is very similar to angular one, but in these cases the patterns is looking like in the some radial direction. That means if you look at the top view, the water will not only moving the along the sidewise, it also have some tributaries in the annular direction. So this is the annular drainage pattern. So these are some typical drainage patterns. And last one maybe the adherence drainage systems. Actually, a adherence drainage system is those one where there is no specific drainage system or pattern is followed. It is something like staggered system. No coherent patterns or of a river or lakes are followed. It's some adherence patterns. The classic example, one example is like the Canadian shield. This is due to the formed in the last ice ages and some abrupt patterns found in this shield. Last one is the angular drainage patterns, where actually the angular drainage patterns are actually occurs in those areas only where the bedrocks, joints, and the faults are intersects more accurate angle than the rectangular drainage patterns. That means in rectangular drainage patterns, due to the bedrock joint and faults, the meeting angle of the tributary is always in 90°. But in angular drainage patterns, and if the meeting angle is more or less in right angle, in those cases the angle will be more or less 19. The pattern will be same as like as rectangular, but the meeting angle will be something more or less 90°. So this is another variant of rectangular drainage patterns. Actually, up to this, these are the some basic discussion of the different types of drainage patterns. And next class, we will discuss some stream ordering systems for our simplicity of calculation. So we need to classify or analyze the drainage patterns of an area to easily classify and for the future research purpose or anything else. So there are some methods for ordering the streams. That means to understand how the stream order is. That means the stream order is actually directly denotes that the higher number of stream order means the river have higher large catchment area and huge number of tributaries, etc. That means the order of tributaries. So later we will discuss how there are some methods, and along these methods we also only discussed the one in our syllabus, the Horton's stream ordering and Strehler's stream ordering. These two are actually included in this course. And now we will discuss some we'll show some map on the drainage system of Bangladesh and the adjacent areas. The first one is the Ganges Brahmaputra Meghna GBM basin, most commonly known as the GBM basin, and it's the Ganges Brahmaputra Meghna. It's simply Brahmaputra. Maybe it starts from the China and then it moves to Nepal, India, then Bangladesh, and go on. So for our country, as we are in the lower side of the tributary, very ending lower side to the tributary. So all the waters are collected from the upper areas, and thereafter it will be moved. Just a minute. Okay, sorry for interruption. So this is an view of Ganges Brahmaputra Meghna ZVM basin system, and here are some tributaries, and it this is the boundary of this river, and the yellow one, this actually the tributary is the boundary of Ganges. This one is for Brahmaputra, and on small this portion, this is for Meghna. So that over entire area is known as the ZBM basin system. And here are some view of the drainage basin of Bangladesh. Different colors actually color legend represents the first one is the Brahmaputra Jamuna basin. The different basins are actually works in the Surma Kushiara for the Sylhet region. And the basin of the Chittagong region, these actually Karnafuli, Muhri, etc. These rivers are actually served. So these are the four major basin in Bangladesh, one by one. The first one is the Brahmaputra Jamuna river system, the upper portion, Rajshahi, Chapainawabganj, Dhaka, this zone. The next one is the lower portion. This is the Ganges Padma river basin system, the lower portion, including the Khulna, Borishal, Patuakhali, this coastal area. So this is the Ganges Padma river system. Next one is the Ashurma Meghna river system. This is the upper right portion, including the Sylhet, Mymensingh, Kumilla, this zone, Noakhali, this zone. And the last one is the Chittagong region river system, the lower right portion, including the hilly region, Chittagong hill tracts, now Teknaf, etc. So here are some common river, Halda, Kornofuli, Ichamoti, and then some Naf river. Also, Naf river is actually the sharing river, including Bangladesh and Myanmar. So this is the sharing one, and also with some Shangu, Matamhuri, etc. Some small hilly rivers. So these are actually covered this area. This is the Chittagong river system. So here are some typical view, and hopefully next class we will discuss the different types of different methods and how we can calculate the drainage patterns, a number, stream ordering, and stream number for different drainage patterns. Okay, so hopefully this is our discussion, and now if anyone having question, you may ask. And I already, so class for today's lecture, the class is closed. Now I'd like to show the submitted assignments. Actually, I'm just showing the numbers if anyone is missing. Here are some irregular students, 12, 18, and some students were from 16 batch, 1791, and thereafter roll number 26. Maybe he is absent also in the last course, CE-201. So I found him absent, and now roll number 43. Roll number 43 কি আছে? 44 দেখা যাচ্ছে। 43 কি ক্লাস করে তোমাদের সাথে?
জি স্যার, করে স্যার।
আচ্ছা, তার মানে হয়তোবা সে তাহলে সে প্রেজেন্ট বাট সাবমিট করে নাই। আর এরপরে বাকি যারা আছে সবাই মোটামুটি সাবমিট করছে। 62 সম্ভবত নাই না পার্মানেন্টলি?
স্যার নাই স্যার।
আচ্ছা, 62 নাই। এরপরে আমি আরেকটা রোল নাম্বার দেখলাম, না বাকিগুলা ঠিক আছে। হ্যাঁ, বাকিগুলা মোটামুটি ঠিক আছে, প্রেজেন্ট আপ টু 131। তো মোটামুটি এই তো 43 একজনই তাহলে সাবমিট করে নাই, সেটা আমি রোল নাম্বারটা পাইছি। তো ঠিক আছে
স্যার, একটা কথা ছিল স্যার, নোটিস।
বলো।
সবার উদ্দেশ্যে আজকের ওই যে ফ্লুইড লাইন কাজটা হবে না।
আচ্ছা, হ্যাঁ, আমি মেসেজ তাই তো। হ্যাঁ, বলো কি বিষয়
স্যার? আবার একটু স্যার দেখতে পারি স্যার একটু।
129।
জি স্যার।
এখানে আসলে মার্কস আমি দেইনি, আমি জাস্ট যারা অ্যাবসেন্ট গুলাকে সর্ট আউট করছি। যদি কারো এখন যদি ওর আমি দেখলাম যে একজনই খালি সাবমিট করে নাই, 129 সাবমিট করছে। হ্যাঁ, আমি মোটামুটি চেক করছি, তোমার যারা আছে সবাই সাবমিটেড, শুধু একজন সম্ভবত আর যোগাযোগও করে নাই, যার কারণে আমি জাস্ট ক্লারিফিকেশনের জন্যই চেকটা করলাম। তো ঠিক আছে, আমার সাথে হয়তো বলো।
থ্যাংক ইউ স্যার।
ওকে, আর নেক্সট হচ্ছে আমি তোমাদের একটা ক্লাস টেস্ট নিব। ক্লাস টেস্টটা হচ্ছে তোমার হোপফুলি এই ড্রেনেজ বেসিনের উপরেই হবে। সো ড্রেনেজ বেসিনের উপরেই ক্লাস টেস্টটা নিব, এবং এই ক্ষেত্রে হয়তো বা ম্যাথমেটিক্স থাকবে। আমি তো ম্যাথ করাবো ড্রেনেজ বেসিনের, তো হোপফুলি ম্যাথই থাকবে। সো এটা একটু হয়তো বা নেক্সট উইকে আমি ক্লাস নেওয়ার পরে টাইমগুলো তোমাদেরকে দিব। আর একটা টপিক আমার থাকবে জিওলজি অফ বাংলাদেশ, ওইটা একেবারেই তোমার হচ্ছে থিওরি। তো আমি হয়তো বা একটা বা দুইটা ক্লাস মোটামুটি ডিসকাস করে দেন একটু বইয়ের কপি আছে আমার কাছে থিওরি, ওই কপিগুলো দিয়ে দিব, মোটামুটি পড়ে নিবা। এটা একটু জাস্ট তেমন একটা বোঝার কিছু নাই, শুধু থিওরি। তো মোটামুটি পড়ে নিলে হোপফুলি হবে। হ্যাঁ, তো মোটামুটি আমার পার্টটা শেষ হবে। এরপরে হচ্ছে ম্যাডামের সাথে কথা বলে ম্যাডাম এবার বাকিটুকু কমপ্লিট করবে আর কি। তো ঠিক আছে, আমি আবার নেক্সট ওয়েডনেসডে ক্লাস নিব আশা করি। তাহলে আজকের ক্লাসটা ক্লোজ করতেছি। তোমাদের কালকের লেকচারটা মনে হয় দেওয়া হয় নাই, আমি আজকে এটা সব একসাথে দিয়ে দিব।